Hello everyone! Thank you for attending the BAS Electrochemical Webinar 2022 Winter. I'm Miho from International Research Team, and I will be the moderator. And today I will be presenting the second part. Before we start, as usual, we will ask you to don't be worried to record and enjoy the webinar. We are recording and will send the directions to you as soon as it is ready. In this way, you will be able to review the full webinar. Also, if you have any question, please feel free to contact us. Well, let's start today's webinar. The first part will be introduced by Professor Noriyuki Watanabe, a former assistant professor of the Faculty of Engineering at the University of Tokyo and BAS Technical Advisor. The theme is Reference Electrode Basics.
Today's title is like this, reference electrode. This is also essential part in electrochemistry. Requirement for reference electrode, extremely small change in potential during long time. Reversible and large exchange current. That means very fast electron transfer. This is a very important part for reference electrode. Various kind of reference electrode is available. For example, non-soluble HHCl, HG2Cl2, HGO, HGSO4, and a soluble hydrogen electrode, copper-cuprous sulfate, silver ion. This copper-cuprous sulfate is usable corrosion field for aqueous. For non-aqueous it's Ag plus electrode. Another is a pseudo reference electrode, platinum. But platinum is not definite indicator, depending on the experimental condition. I will mention about this kind of Ag reference electrode. AgCl electrode is the most standard electrode, most usable in this electrode. Ag is metal wire, and chloride ion is solid. This reaction requires that constant electron potential. This is a schematic figure of this HHCl electrode. The Ag wire is coated with HCl salt on Ag wire surface. This wire is immersed in potassium chloride, saturated potassium chloride aqueous solution. For saturated condition, KCl salt is also existent in solution. The bottom is flat, so chloride ion can pass this flat. The electron potential is presented in this equation. This H plus standard potential, and this is term depending on activity of Ag plus ion. This standard potential is presented like this. This solubility, Ag ion and solubility product of so depending on chloride ion, chloride solution, and solubility product coefficient. So this the simplified presentation. This E0, this term is constant, 0.222 volt. For HHC electrode, potential of HHC electrode depends on the activity of chloride ion, depend on chloride ion. Another reference electrode is electrode. It is composed of mercury and mercury chloride. Reaction is like this. And this caramel electrode, schematic presentation of caramel electrode. This high mercury, and it's mercury salt, H2Cl2, and this KCl solution. This looking tube to escape the contamination from chloride ion. This looking tube is usable. This commercial available mercury electrode, caramel electrode. The reaction about mercury and mercury divalent ion is the potential representation is like this. A standard potential, and depending on the Hg's concentration. So this case is very small number, very small. So very insoluble salt. This so this finally depending on the chloride ion like this, and this term is constant, and the total potential depends on chloride ion concentration. Mercury oxide electrode is usable for alkaline solution. Electron reaction is like this, and in alkaline solution, that the reaction scheme is like this, and potential is represented by this equation. These are constant, and depending on total potential is depending on mercury divalent ion content. This electrode is usable for alkaline solution. Very small solubility, very rather insoluble. This term is about 0.1 volt. Standard potential of mercury oxide electrode in various solution, various alkaline solution. Very minor change. There are minor change depending on the salt and content and salt, kind of salt, depending on like this. This mercury sulfate electrode is like this. Solubility product is not so insoluble, but rather medium solubility. This is standard potential, depending on sulfate ion concentration. Here. This value shift to this 640 millivolt or saturated case SO4. How about reference electrode in non-aqueous solvent? Ag plus is nitric acid, acetonitrile typical. This the presentation of silver ion content depends on redox potential is zero, depends on using solvent. Redox potential is specified by comparison with internal standard. So depend on the experimental condition. So there is remaining some part of uncertain to for presentation and universal standard is necessary, such as ferrocene or bisphenol chrome. It's usable for internal standard. Problematic point is low solubility of potential. Solubility of silver salt don't dissolve in dichromethane. Silver ion is reduced in dimethylformamide, including water. So in experimental condition, you need quotient. Dependence of redox potential upon solvent. It's silver ion as reference electrode. If you use Ag plus, there is some uncertainty. So this dichloromethan, the most plus and this most minus. So uncertainty of 1 volt is there is uncertainty between the potential. This ferrocene or this phenylchrome is experimental standard for organic solvent system. So there are some uncertainty in potential scale. So you need to give a comparison to ferrocene or bischrome compound. Rather very big difference between pyridine or dichloromethan. This very this rather polar solvent. This unpolar dichloromethan. Dimso is rather medium polarity. DMF or dimso or acetonitrile. Propylene carbonate is rather non-polar solvent. So propylene carbonate or dichloromethan is such a unpolar solvent compared to methane or ethane or THF or dimso. So you need the value about comparative value of potential using this kind of solvent. About the hydrogen electrode, it's this schematic presentation. This hydrogen gas and platinum electrode, the redox reaction occurs on this surface of platinum electrode, and the potential is defined constantly. We define potential standard 0 volt. This reaction, the standard potential is depend on the, of course, proton content or and hydrogen molecule pressure. Electric potential depends upon activity and partial pressure of hydrogen gas and temperature. So if you describe the potential in your experiment, so experiment measuring condition is needed to present. And this select zero and define E0 standard potential is zero. Electric potential depends upon proton activity and hydrogen partial pressure and temperature. Another reference electrode is copper-cuprous sulfate electrode. This cuprous sulfate and this cuprous sulfate solution. This electrode is usable for corrosion science. Because this system does not include chloride ion. Chloride ion is most avoidable ion in corrosion field. Copper and cuprous saturated cuprous sulfate aqua solution, cuprous sulfate crystal. This potential is like this. And this does not include chloride ion. So this electrode is usable for corrosion science. Boundary potential and salt bridge. Boundary potential depends upon the ion in both solution, and mobility depends on the type of ion. So this solution, the boundary of solution give some kind of potential difference. This Henderson equation, the very complicated equation, that meaning with concentration of ion and this mobility difference of mobility and ion is and also the ion number. Such a parameter is a defining factor of potential junction. This mobility of this mobility is this valence number. So proton is very most fast ion. This mobility depends on the ionic size. So proton is very most smallest ion. So very fast, and the mobility of ion depend on ion size. So very large ion is sulfate or perchlorate. This proton is very small, but hydroxide ion is rather large, affected by large size of oxygen. The mobility of ion is a very defining factor for mobility of ion. This is rather complicated subject, and in most experiments you do not need to consider these parameters. Mobility of proton is very fast. Hydroxide is also ion size determinant. Relative mobility of various kind of ion. Proton is very fast, and this alkali solution. So large size of alkali solution, alkali ion is rather slow. Lithium is fast, and this proton is very fast, and this rather moderate change. This one is fast. About pseudo reference electrode, potential stat has a connecting terminal for reference electrode. It is necessary to inverse connecting terminals such as platinum wire in test solution. It works as an electric connection. Whether it is a real reference electrode or not, don't mind. It is impossible to define potential without electrical contact. So you need platinum for just electrical contact. But it is impossible to specify electric potential only with platinum wire, of course. Occurring inconvenience when impedance of reference electrode increase largely. Increase of time constant. Decrease of bandwidth in potential stat. Generation of noise and or oscillation due to positive feedback. With that, narrowing of bandwidth. One countermeasure, it like this, just potentials that reference electrode and not directly, just with capacity to connect the solution with platinum wire. This is one countermeasure. This is last slide. Summary of various reference electrode. HCl easy to handle, highly versatile. It is very usable. Copper electrode, problem in usage of mercury. Mercury is not recommended use for electrochemistry. Mercury oxide electrode appropriate for usage in alkaline solution. The solubility of mercury oxide is extremely low, so it is contaminates the environment. Ag plus is reproducibility and stability, some kind of reliability. mercury sulfate, good reproducibility, rather not definitely good, but rather good reproducibility with a little bit problem in stability and usage of mercury, but not so big concern. Hydrogen electrode, potential standard, hard to usage. And all the time to use hydrogen gas is not so convenient, rather inconvenient. Platinum wire pseudo reference with small impedance, but short time stability and low reliability. So, but very rather convenient usage. This that's all.
Thank you, Professor Watanabe. The second part will be first electrochemical measurement, selection of electrodes, presented by the moderator. Let's start. For those who are starting electrochemical measurement, here are some points to consider when selecting consumables such as electrodes and cells. First of all, I would like to briefly introduce the electrochemical system. The electrochemical measurement system consists of a potentiostator to control the potential and a cell to hold the sample. This is an example of three-electrode system, with three electrodes attached to the cell: working electrode, reference electrode, and counter electrode. Also not shown in this figure, there is an enclosure to exclude external electrical influence called the Faraday cage. Faraday cage and a rotating electrode device to rotate the working electrode can be added to the system. Voltammetry cells can be broadly divided into two electrode systems and three electrode systems. In a two electrode system, the counter electrode is the reference for the potential, but it has the disadvantage of not knowing the real variation of the potential applied to the working electrode. On the other hand, in the three-electrode system, the reference electrode is the reference potential, and by changing the potential of the working electrode relative to the reference electrode, the electrode potential of the working electrode can be measured and controlled. In the measurement, set the required three types of electrode and the measurement solution, and fix each electrode so that the cable from the potentiostat can be connected. The working electrode is the electrode where the desired reaction occurs. The reference electrode is the electrode that serves as the reference for the electric potential, and the counter electrode is used to close the current circuit in the electrochemical cell. The potential is defined between the working electrode and the reference electrode, and the current flows between the working electrode and the counter electrode. BAS offers various shapes of voltammetric cell. Select according to the sample volume, composition, and characteristics, and the need for temperature control. How much can be a measuring solution be prepared? Is it a large sample volume, such as 100 milliliter or few milliliters? Is the liquid of solution acidic or alkaline? Does it need to be deoxygenated? Is it necessary to control the measurement temperature? Be aware of these points when selecting the voltammetric cell. The first point to consider when selecting working electrode is that working electrode is where the desired reactions be observed occur. Therefore, it is necessary to properly select the material shape and size so that the desired reaction will occur. The key points are to select the material that will take place the appropriate reaction, and also to determine what kind of measurement system will be used. How much surface do you need? What kind of measurement method do you want to implement? In addition, the working electrode is selected in consideration of the total action between electrode and the sample. The second point to consider when selecting the working electrode is to select the material shape and size that will produce the desired reaction to be observed. As the material of working electrode, there are metals such as platinum, gold, silver, copper, etc. Also, carbon electrodes such as glass carbon are available. There are transparent electrodes such as ITO, which is used in semiconductors and spectro-electrochemical measurements. There are electrodes with various shapes, such as plate electrode, wire electrode, mesh electrode, and interdigitated array electrodes. Since the results will differ depending on the size, it is necessary to select the appropriate size of electrode. There are also microelectrodes, which has the ability to perform high-speed measurement. The third point to consider when selecting working electrode is the importance of creating an environment in which the reaction of object to be measured can be observed. Depending on the condition of the sample, there will be cases where a reaction or side reactions occur, which is not desired to occur, and the resulting current makes it difficult or impossible to observe the current of object. This can be caused by the material of electrode, solvent, electrolyte, or solved gas. Therefore, it is important to continue within the range where there is no unnecessary current. The range without such unnecessary current is called the potential window, which is the potential range that can be used for electrochemical measurement of the object to be measured. As shown in the example of a cyclic voltammeter using glass carbon electrode, there is no unnecessary current in the range from about minus 0.8 volts to 1.2 volts. This is the range in which the sample current can be uninterrupted. In the voltage range below or above this range, various side reactions occur, making it difficult to see the current value of the desired reaction. As the fourth item when selecting a working electrode, we would like to introduce the potential window of various electrodes. In an aqueous solution, the potential window shifts depending on the pH of the solution, and the platinum electrode has a potential window in such a region. The mercury electrode is characterized by a narrow oxidation window, but conversely, it has a wide reduction window. The carbon electrode has a relatively wide potential window for both reduction and oxidation. In non-aqueous solutions such as acetonitrile and dimethyl-formamide, the potential window is wider than in aqueous solution, example carried for platinum electrode. The following is an introduction to the features of platinum electrode as a material for working electrode. Platinum electrode has high purity and high corrosion resistance. It has high catalytic activity in various electrode reactions. In addition, the electrode surface area can be calculated from the absorption of hydrogen ion. On the other hand, the problem with platinum electrode are the platinum itself is expensive, and the range of potential that can be used in aqueous solution is limited because of the tendency of water reduction and decomposition. The characteristics of glass carbon electrode are as follows: chemical resistance and relatively hard, low cost compared to precious metals. It is relatively easy to modify and modify the electrode surface. In addition, the range of potential can be applied. The potential window is relatively wide. The points to note are as follows: carbon can be oxidized and electrode performance can be degraded, so care must be taken when cleaning the electrode surface. Also, note that a large positive potential, a large oxidation current, is applied and the electrode surface may be damaged. Depends on the material of electrode, the reaction may occur more easily. This is because the electrode acts as a catalyst, and it is called an electrode catalyst. It is known that hydrogen ion reacts more easily when platinum is used. The electrode material also has various physical and chemical actions. For example, the gold electrode has the characteristic that it is easy to attach molecules with sulfur. So, it is necessary to carefully consider and select the electrode necessary for measurement. If a working electrode is used, it will gradually deteriorate due to the absorption of substance to the electrode and deterioration of electrode surface. Therefore, it is necessary to clean the surface of working electrode before the electrochemical measurement. The cleaning method is as follows shown: physical polishing of electrode, chemical cleaning, electrochemical cleaning, chemical cleaning, ultrasonic cleaning, and etc. Electrochemical cleaning, chemical cleaning, and ultrasonic cleaning may cause cracks and corrosion of electrode, so we basically recommend the physical polishing. BAS can offer the polishing kit as a PK3 electrode polishing kit. Next, in this section, we will briefly explain the Features of reference electrode. The reference electrode is an electrode used in a three-electrode system to define the potential of working electrode. The most important feature required of the reference electrode is that it must exhibit a stable potential. By showing a constant potential, it becomes possible to observe the desired reactions by specifying the voltage applied to the working electrode with a potentiostat. Here is a picture of an example of a reference electrode. This is the silver chloride electrode. At the top is a metal terminal for connecting to the device and potentiostat. Below, there is a silver wire, which is covered by silver chloride. The internal solution contains chloride ion, and this kind of chemical reaction equilibrium maintains a stable electric potential. Here we will introduce the main electrodes that can be used in aqueous solution. First, the standard hydrogen electrode. This is the reference electrode for all electrodes and is determined to show 0 volts at any temperature, although it's very important for electrochemistry. It's rarely used in practice because it can be used only in a concentrated hydrochloric acid solution, and it is difficult to handle because it requires the flow of gaseous hydrogen. On the other hand, reversible hydrogen electrodes are designed to be used at the same pH as that of the sample, and we offer such electrode as shown here. Our reversible hydrogen electrode is easy to handle because the pH can be freely selected in the neutral to acid range and hydrogen gas can be stored and used. However, it is important to note that the potential of this electrode decreases about 59 millivolts with respect to standard hydrogen electrode for every 1 increase in pH. These electrodes are often chosen when you want to use an electrode that is close to standard hydrogen electrode, or where you want to use it to evaluate reduction catalyst for full cell because the reaction mechanism is similar. Next are silver chloride and calomel electrodes. Silver chloride electrodes are widely used, especially silver chloride electrodes that do not use hydrogen. The silver chloride electrode, when using saturated potassium chloride as the internal solution, shows 198 mV for standard hydrogen electrode. When indicating an electron with respect to the same standard, it is written as Vs versus like this. The calomel electrode is a mercury electrode, which shows 242 mV for standard hydrogen electrode. The calomel electrode is also a stable reference electrode, but since it uses mercury, it has become less frequent use in recent years. For general measurement, the silver chloride electrode should be chosen. For non-aqueous systems, where organic solvents are used instead of water, you can use the Re7 silver ion electrode, as shown here in addition to the silver wire. Please note that the reference electrode for aqueous solutions cannot be used for non-aqueous solution. This electrode consists of a glass tube filled with solution containing silver nitrate and silver wire immersed in the solution, and can be used in any solvent that suits your sample. For non-aqueous solvents, IUPAC, an organization that sets chemical standards, recommends that the final potential be reported based on the ferrocene substance. What this means is that, as shown in the lower right figure, the potential of a sample is first measured using a reference electrode. Next, the potential of ferrocene is measured with respect to the reference electrode. The amount is corrected, and the potential of a sample is reported with respect to the potential of ferrocene. Here is a brief explanation of the role of the counterelectrode. The counterelectrode is an electrode where the current flows in the opposite directions to the working electrode, and the role is to close the current circuit. At this electrode, the opposite reactions to that of the working electrode takes place, and if an oxidation reaction occurs at the working electrode, a reduction reaction occurs at the counterelectrode. There are two requirements for the counterelectrode. It must not react and causing contamination, and it must have a large enough electrode surface area to allow the current to flow. In order to satisfy these two characteristics required of counterelectrode, materials such as platinum, silver, and carbon are often used. In addition, the shape must have a larger electrode surface area than the working electrode, such as a straight wire or coil shape. One thing to keep in mind when using the counterelectrode is to keep a sufficient distance from the working electrode to prevent a short circuit. In addition, in order to prevent contamination of the solution or to prevent unnecessary reactions, it will be necessary to take measures such as isolating it from the working electrode using a double junction chamber. This concludes the introduction of some points to consider when selecting consumables such as electrodes and cells, for those who are starting electrochemical measurements. I hope you enjoyed the webinar. If you have any question regarding to the webinar or other topics, please feel free to contact us. The email is here. Also, you can watch here in the BAS channel a variety of movies, including the past webinars, and you can follow and have access to the latest news. The next webinar we are working out to have for April. For today, thank you again and stay safe and healthy.